The next electric vehicle shortage may not come from batteries. It may come from a material most buyers will never see. A product can be fully designed, fully funded, and already scheduled for launch, and still be impossible to ship because one approved material, buried 3 layers down the supply chain, did not arrive on time. The delay can look different in every industry. In an electric vehicle, it may be hidden inside the motor. In robotics, it may show up inside an actuator. In precision optics, it may be the polishing material that decides whether a lens or sensor meets tolerance. And in defense, it may be a qualified component inside a radar system, a guidance unit, a drone, a missile, or an aircraft platform. That is the rare earth problem. It is not just about rocks in the ground, and it is not just about magnets. It is about whether difficult materials can be turned into trusted industrial performance, repeatedly, at scale, and on time. That is why the numbers look strange at first. Rare earths are used in small amounts, but the industries sitting on top of them are enormous. The International Energy Agency has warned that expanded rare earth restrictions could put around $6.5 trillion of downstream production outside China at risk. That number is not the value of the minerals themselves. It is the value of the industrial activity exposed to a small but critical input. The risk is that a small material can sit underneath cars, aircraft, electronics, defense systems, energy equipment, data centers, and advanced manufacturing. So ownership of the mine is only the first question. The harder question is whether that material can be turned into something a factory is willing to trust. Because a mine gives you material, modern industry needs qualified performance. And the gap between those two things is where the real rare earth bottleneck begins. That gap is easy to underestimate because rare earths rarely appear in the final product story. A car company talks about range, charging speed, software, and design. A robot company talks about artificial intelligence, vision, and movement. A defense contractor talks about capability, precision, and reliability. A wind turbine company talks about clean power and long-term output. But underneath those public stories, engineers and procurement teams are dealing with a quieter question. Can the exact material required for this system be supplied, tested, certified, and delivered without breaking the production plan? That is where rare earths become a factory logic story. They are performance materials. In small amounts, they can help machines move more efficiently, glass become clearer, catalysts work better, sensors become more precise, and critical systems become smaller, lighter, or more reliable. Most products do not use huge quantities of rare earths. That is not the point. The point is that some materials matter because of where they sit inside the system. A few grams in the wrong place can change the cost, weight, heat, efficiency, or reliability of the entire machine. Take electric vehicles. The public sees the battery pack, the screen, the software interface, and the range number. Inside the company, the motor is where the rare earth question becomes real. A strong permanent magnet can help make a motor smaller and more efficient. If the material becomes more expensive, less available, or harder to certify, the engineering team may have to consider a heavier motor, more heat, a different cooling design, or a performance trade-off the marketing department never wanted to explain. That is not a chemistry footnote. It is a product decision. If the motor changes, the vehicle may change. If the vehicle changes, the cost model may change. If production is delayed, the issue no longer belongs to engineering alone. Finance has to model the impact. Sales has to manage delivery promises. Procurement has to renegotiate supply. The factory has to ask what can still be built this quarter. This is how a material issue becomes a business issue. The same logic appears in robotics, but the pressure shows up differently. Humanoid robots are usually presented as an AI story. Better models, better vision, better control software. That is only half of it. A robot still has joints, and those joints need actuators. Actuators need motors, sensors, gears, materials, and heat management. A prototype can use expensive parts and still look impressive on stage. Mass production cannot. Once a company tries to build thousands of robots, every material choice becomes a cost, reliability, and supplier decision. A small change in a motor can affect weight, power use, heat, repair rates, and the price of the whole machine. That is the difference between a demo and an industry. Rare earths also matter in places that do not look like motors at all. In precision optics, rare earth materials can be tied to polishing, glass, lasers, and display performance. That matters for cameras, sensors, medical equipment, scientific instruments, semiconductor tools, and defense systems. In catalysts, rare earths can help chemical processes run more efficiently. That can affect refining, emissions control, industrial processes, and environmental systems. These uses are less visible than an EV motor, but they show the same pattern. Rare earths often sit in the layer that helps another system perform better. They may not be the largest input by weight, but they can become the input that determines whether the final product meets its specification. That is why replacing this supply chain is so difficult. People say, find another source. It sounds simple until you ask which layer of the chain you are talking about. A country may have rare earth deposits, but that does not mean it has large-scale separation capacity. A company may produce oxides, but that does not mean it can produce metals, alloys, magnets, polishing compounds, or catalyst materials at the quality a customer requires. A new supplier may have a factory, but that does not mean automakers, aerospace firms, medical equipment makers, or defense contractors have already approved its materials. In manufacturing, a material is not useful simply because it exists. It becomes useful when an engineer can design around it, a factory can use it repeatedly, a customer can approve it, and a purchasing team can count on it arriving on time. That trust is slow to build. A mine can be announced in a press release. A qualified material supply chain cannot. Process stability is earned inside plants. Customer qualification is earned through audits, failed batches, retesting, quality reports, and long conversations between engineers and customers. Supplier confidence is not declared. It is built slowly through delivery after delivery. This is why the middle of the chain matters more than most headlines admit. The International Energy Agency's data makes the point clearly. China's share of mined magnet rare earths is large, but its position becomes even stronger further downstream, in refined output and sintered permanent magnets. That is where leverage forms. The mine matters, but processing, refining, material quality, and customer qualification often decide whether the material can actually enter the economy. And when that material becomes uncertain, the damage usually begins quietly. A supplier warning lands in procurement. Engineering asks whether the material can be replaced. Finance calculates the cost of delay or redesign. Production planning asks what can still be built this quarter. Sales worries about customer promises. By the time the issue reaches the boardroom, it is no longer a raw material problem. It is a delivery problem. And in manufacturing, delivery is where strategy becomes real. Defense shows the same issue in a more serious way. A fighter jet, missile, drone, radar system, submarine, or secure communications device is built from parts that are tested, documented, and qualified over long timelines. If a rare earth-dependent component becomes unavailable, the contractor cannot casually switch suppliers and move on. A replacement part may require new testing, new documentation, system validation, and risk approval. A delay in a consumer product hurts sales. A delay in defense can affect readiness. That is why governments are putting money into refining, recycling, and critical materials projects. The goal is not only to own more rock, it is to rebuild the capability that turns difficult materials into qualified industrial inputs. Recycling is part of that discussion, but it is not a shortcut. Old motors, used magnets, industrial scrap, and discarded electronics can become feedstock. But the material still has to be collected, separated, purified, processed, tested, and accepted by customers. Recycling is not a way around the supply chain, it is another supply chain. Substitution has the same problem. Sometimes another material can work, some motors can be redesigned, some applications can use ferrite magnets, some products can reduce rare earth content, but substitution is not free. A different material may add weight, reduce efficiency, increase heat, change the cooling system, or force a redesign. After that comes testing, certification, and customer approval. The question is not whether an alternative exists on paper. The question is whether it works inside the real product, under real conditions, at the right cost, and in time for production. That is why rare earths should not be treated as a simple resource story. The real pressure shows up in timing, qualification, cost, and control over manufacturing decisions. But more than that, they reveal how modern industry actually works. The future may look digital on the surface. Electric vehicles are sold as software on wheels. Robots are sold as artificial intelligence with a body. Wind turbines are sold as clean energy. Defense systems are sold as advanced technology. But underneath, the future is still physical. It depends on materials that must be mined, processed, refined, tested, shipped, certified, and trusted. A company can design the future on a screen, but it still has to build the future on a factory floor. That is where rare earths become a factory logic story. They reveal the hidden middle between a raw material and a finished machine. They show why the most important part of an industry is not always the most visible part. And they explain why control over performance materials can become control over production itself. The next industrial race will not be decided only by who designs the best machine. It will be decided by who can turn difficult materials into reliable performance, repeatedly, at factory scale. That sounds like a mining story. It is not. It is a manufacturing control story. Because in modern industry, a machine is not real when it is designed. It is real when the supply chain can build it again and again. This is factory logic.